everyone. In this video, we are going to solve the recent questions from your physics unit 2. Now, for this part of your section, we're only going to solve the waves theory. So waves are again further categorized into 4 sections, that is properties of waves, standing waves, polarization, and phase and path difference. So we are going to start with standing waves first. So this is a question from standing waves from the year 2019 October. So let's start with this. It says that an Iolene harp is a stringed musical instrument that is played by the wind. And Aeolian harp is known in the is shown in the photograph. This is your entire sound creating whatever this is, and when air passes through the strings, it forces them to vibrate, creating a stationary waves on the strings, and explain how stationary waves are formed in the strings. Now this is not related to anything on with this specific harp. This is entirely repeated memorizing theoretical questions for unit 2. They want you to find out, like they want you to describe how stationary waves are formed, and they're going to give you 2 marks for this. This is a very common repeated questions in most of the papers. So I'll just write again RQ over here, and the answer over here should be, for standing waves to create, you have to think of it in this way, that one wave will pass out, and the reflection of the previous wave will also pass out through the same string, right? So 2 waves traveling in opposite directions, and um, they are going to either superpose or interfere in some cases, right? I mean, if they're going to interfere constructively, you hear loud sounds. If they interfere destructively, you hear low sounds. But not that much detail is involved over here, because it only is giving you 2 marks. So only referring that 2 waves traveling in opposite directions and causing interference to occur, right? That is the only information that you need to know, that you need to describe for this kind of very small questions. If this same question was asked, and if the marks was increased to 4 marks or 5 marks, then you would include the definitions for your construction and destruction, like constructive interference in phase, in path difference of n lambda, destructive interference in antiphase, in path difference of n plus half lambda. That would be included in that situation, but not now over here. So we will start. It says over here that 2 waves, we're just going to write that 2 waves traveling in opposite directions, causing them to superpose. Now again, if you want this file either written or blank, you have to join our Discord link. The description will be added in this description box for this video. Okay, and this is a repeated question. We will actually see a lot of repeated questions in unit 2, because unit 2 is like 60% theory, 40% maths. So theory, they cannot change from the theoretical part, right? So I would suggest list down all the theoretical questions and try to memorize the answers for this, because these are like easy free marks that Edexcel is giving you guys. Okay, then for part B, it says that when the strings of an Aeolian harp vibrate, the frequency f of the string vibration is given by the equation this, and where u is the speed of the air moving, and d is the diameter of the string, and k is the constant, which so show that the constant k has no unit over here. Okay, in order to show that, I just have to like rearrange and make k the subject of this equation, and that would be what? If d divided by u, and I can write this as f d with 1 over u. In this case, frequency is hertz, but hertz is a derived unit. You have to break down hertz in its base unit, which is going to be 1 over second, and distance is meter. Velocity over here is itself meters per second, which is going to be 1 over meters per second. That can be written as 1 over meter. So 1 over second with meter. Okay, so obviously this meter per second in the denominator is going to get inverted, and finally this second gets cancelled out, meters gets cancelled out. Finally, you're going to left out with just 1, right? So that means obviously in this case the k over here, the constant k, doesn't have any unit, right? It doesn't have any unit over here. Everything gets cancelled out at the end of the calculation. Okay, and then we'll move on to the next question. This is again for standing waves. This is from Jan 2020, and it says that an experiment is carried out to investigate the speed of transverse wave on stretched string of length L. The vibration generator causes the string to oscillate so that the stationary wave is produced. The frequency of the vibration generator is adjusted until the pattern shown in the diagram is produced. Okay, we can clearly see over here you have two complete wavelength, right? That is being used to create this entire pattern. How can you understand? This is the start. Wait 1 minute. This is the start. This is the end for one complete wavelength, and this is again the start and end for the second complete wavelength. So from this part, this is one complete wavelength, and then again this is one complete wavelength. So the entire length of the string is now being used to create 2 lambda over here. So L is actually used to create 2 lambda. Okay, now and again this part, it says that determine the wavelength. I can clearly understand that what would be the wavelength, right? The entire length of the string is used to create 2 lambda. So lambda over here is going to be L over 2, which is 1.70 over 2. And if you calculate this, it will give you the final value for your case, which is 1.7 by 2, that is 0.85. So that is the, sorry, I wrote 8.85, 0.85 meter. That is the value for your total wavelength in this part. Okay, then we'll move on to the part C. Part C was related to part 1, so that's why we attached that part A over here. The frequency of the vibration generator is reduced until the wave pattern is shown below is produced. This time again I can understand this is one complete wavelength, right? Obviously, as we are using the same string, the length will not be changed, right? So the length is still that 1.7 meter, and now it is creating one wavelength. So entire length is now used to create one lambda. That means now over here lambda is your 1.70 meter. Okay, another thing, explain the effect this would have on the speed of the waves on the string. Okay, it says that the frequency of the vibration generator is reduced. There are two hints over here. That is, frequency of the vibration is reduced, and one hint was that previously your wavelength was 0.85, now it is 1.7, right? When previously wavelength was half of the total length of the string, now the wavelength is equals to total length of this total string. So that means now wavelength has increased, frequency has decreased. If you remember the equation, F is equals to F lambda, sorry, V is equals to F lambda. From this reduction, frequency decreases, and from this value for wavelength increases, right? So at the end of the day, what happens, by how many units, whatever units your frequency is decreasing, that will be balanced by the increase in wavelength. So at the end of the day, they will balance each other out. So which means velocity is now going to stay the same. That is one of the answers. You could have also arranged the answer using the other equation, which is that mu and tension. Now for that mu and tension, you could have arranged that for velocity again, the formula was what, tension over mu, right? And in this case, as you're using the same string will have the same tension, and same string will have the same mass per unit length. So tension and mu will not change over here. So if there is no change in the tension and mu, in that case also your velocity will not change. So velocity is dependent on two formulas, that is F lambda and one with that tension and mu. So the other formula was V is equals to tension over mu, everything under root, right? So since tension and mu is going to remain same for this entire scenario, so if there is no change in tension and mu, velocity is not going to change. So there are two possible answers for this question. First is in terms of velocity and frequency, that is the decrease in frequency is covered by the increase in lambda, therefore V does not change. That is one possible answer. Another possible set of answers for this would be tension and mu remain same, so velocity does not change. So velocity does not change. Okay, this is the final answer. We will now move on to part 17. It says the student investigated how the frequency of vibration of a string varies with tension in the string, and the student connected masses to one end of the string and attached the other end to a vibrator as shown, and a signal generator connected to the vibrator. The signal generator was adjusted until a stationary wave was produced on the string. The stationary wave had nodes at both ends of the vibrating length and the string L, and an antinode in the middle. They explain how nodes and antinodes are created. This is again a repeated question over here. So we're going to write this, that when two waves are traveling in opposite directions, and they're meeting like they're going to meet it one with one another's reflection. Right? In that case, there will be nodes created at the point for zero amplitude, and there will be nodes created at the point for maximum amplitude. So antinodes for maximum amplitude. At nodes, usually destructive interference occurs, and at antinodes, usually constructive interference occurs. So this is very much repeated questions. I would suggest, memorize the 3 points I'm going to write in the answer over here. So we'll write that two waves traveling in opposite directions two waves traveling in opposite direction, and when they interfere, and when they interfere maximum amplitude, there will be points of maximum amplitude causing constructive interference known as antinodes. And at points of minimum interference, and at points of minimum interference, and at points of minimum amplitude, causing destructive interference, causing destructive, and at points of minimum amplitude causing destructive interference at nodes. Okay, these are the definitions for nodes and antinodes. Again, I should refer to one diagram. This is an extra not related to this question. I'm just explaining this for a further more clear knowledge about nodes and antinodes. Okay, now this is how a standing wave would look like, right? Now these are your points of nodes. This is node 2, this is node 1, and this is node 3, and these are your antinodes, antinode 2, antinode 1. Okay, now it was already stated that antinode 1 is at the maximum amplitude, so this is your maximum amplitude, and node is always on your equilibrium position, or always on the minimum amplitude. So these are your minimum amplitude. always remember in the next exact stage, the wave will actually move in the downward direction, right? For this point, like this sections between all the points between node 1 and node 2. If I label down all the points between node 1 and node 2, they will all move in the backward direction in the next exact second. Right, so what you can suggest from this part is that all the points between node and node 2, as they are traveling in the same direction, so they are in phase. But if you find out and from points node between node 2 and node 3, they are going to move in the downward upward direction, right? As you can see from the figure, in order to be in this stage, they need to move in the upward direction. So all the points between node 2 and node 3 will move in the upward direction. Now, thus for this part, another thing to focus on, all the points before on either side of the node, on either side of a node, the points are in antiphase, because this one will move downward and these ones will move in the upward direction. So there is like two statements you have to focus on. First one is that all points between adjacent nodes are in phase as they travel in same direction, and all points on either side are in antiphase as they travel in opposite directions. Opposite directions. Okay, now after this, this is like an extra notes, so I will just keep it in a different box. Again, if you guys are interested to get this file, please join my Discord link to get access to these files. Okay, now we'll move on to the next part. It says that the student has the weight W Newton applied to the string and adjusted the frequency F of the signal generator until the same stationary wave was set up on the string. The student plotted a graph of frequency square against W. Explain why the graph was a straight line passing through the origin. This is an extremely important question again, and this is kind of related to your Unit 2 materials. Whenever they ask you that the graph will be a straight line, that means you have to connect whatever the equation you are going to create with this y is equals to mx plus c over here, right? Now, in this situation, what we can do is that we have to connect weight with frequency, right? So weight with weight, I mean, over here, weight will obviously create a tension in the string, right? And that tension will be equivalent to weight as the object was not in motion, right? So over here, weight is actually equivalent to tension. So let me just write down the walkthrough first. That tension is equivalent to weight. That means if tension is equivalent to weight and frequency is equivalent to your what was the value? Frequency was equivalent to v by lambda, v by lambda. In that case, now I can suggest the equation was v is equals to, so v is equals to tension over mu root. Instead of writing tension, instead of writing v, I can write, instead of writing v, I can write f lambda. So in that case, f lambda is equals to t by mu root. And again, I don't need to write tension over here. I mean, I don't need to write tension over here. I can write weight in this case because tension is equivalent to weight. And then again, I can understand that F is actually going to be equal to 1 over lambda multiplied with weight over mu root. And in this case again, as I already know, I was trying to create f square on the y-axis, right? So I think it would be better if I take this square to the right hand side. Then I will have f lambda whole square is equals to w over mu, which means now you're going to have F square is equals to weight over lambda square mu. And then again, I am going to get lambda square was frequency square 1 over lambda square with 1 over mu multiplied with weight. Now this is exactly in the form of y is equals to m x plus c. This entire thing is your gradient over here, right? 1 over lambda square, 1 over mu is going to be considered as your graph's gradient. Then again, go back to your question. It was stated that explain why the graph was a straight line, because the question that you're going to create, this is resembling the shape of a straight line. Y is equals to mx plus c, and y it will pass through the origin because it doesn't have any y-intercept. I mean, this equation doesn't have any plus c any value, right? So obviously it will be a straight line. This is the entire walkthrough, but we'll obviously arrange it in a better way in the given space. We will consider that the only force acting is weight, so weight becomes tension. Only weight acts downward, therefore weight is equals to tension. And we're also going to rearrange the equation for velocity. That velocity is equals to f lambda. Therefore, f lambda, I mean I should write that first, the original equation first. V is equals to tension over mu root, which is basically going to be f lambda whole square w over mu. And after that I can write f square 1 over lambda square 1 over mu. I can write directly 1 over lambda square mu multiplied with weight plus c. So plus 0 over here. Now we can write this is exactly in the form of y is equals to mx plus c. Therefore, the graph should be a straight line for frequency square against weight, and as it doesn't have any y-intercept, so should pass through the origin, right? So this is your final statement. So the graph for f square against w should be a straight line passing through the origin, as it doesn't have a y-intercept. As it doesn't have any y-intercept. Now this was, I mean the writings I did over here was just a rough working, so I will not consider that as part of your answer, okay? So I'll just separate this. This was rough working. Now, I would suggest this is not a repetitive question, but this is kind of like related to your Unit 3 materials, right? Descriptive questions that would come across in your Unit 2 based on your Unit 3 questions. So I would suggest, not memorize this, but understand the procedure, how I created the equation from whatever the statement they have provided me. So this is a very important question, expected. I'm going to write it as. Okay, then let's move on to the second part. Describe a method that can be used to confirm that the frequency value stated on the signal generator is correct. Okay, now this is again a repetitive question. In order to measure the frequency of any stated value, I will use a cathode ray oscilloscope, because from the cathode ray oscilloscope, the x-axis will give you the time period for one complete wave, and then I can use the equation f equals to 1 over time to calculate the final frequency to actually confirm that if the stated frequency is true or not. In that case, the answer should be that using a cathode ray oscilloscope, sorry, cathode ray oscilloscope and measure the time period for one complete wave, then using F equals to 1 over capital T, calculate the frequency. Right. Now again, very focus on the terms that for measure and calculate are, we're not using that for both the cases, right? We're only using measure when we're actually going to, like, measure the time period from your graph, from your screen of auto cathode ray oscilloscope, because you're not using any calculator, we're not using any formula for that part, right? You are manually measuring the time period of a complete wave. And for the calculation part, they have their own built-in calculative formula, and you're just going to input the data to calculate the final product or final result. So always remember, use the word calculate when you have formula, and use the word measure when you have to manually find out the value. Okay, this was it. Again, this is a repetitive question, like how to measure the frequency for a wave. This is a repetitive question. Okay, this is RQ. Okay, that's it. We'll move on to the next part. Then this is polarization. I actually couldn't find any more questions from standing waves, so we'll start with polarization. So this polarization says that a filament lamp is a source of unpolarized light, and a polarizing filter is placed between a filter lamp and an observer. The filter is rotated in the plane perpendicular to the direction of travel of light. Which of the following is observed as the filter is rotated at an angle of 90 degree? Now, rotating at an angle of 90 degree will create any change if that light from that filament lamp was polarized, right? If it was polarized, that means it would be only vibrating in one plane. Then rotating that filter by 90 degree would cancel out that one plane, and eventually the intensity would drop down to zero. But this time, as you're working with unpolarized light, unpolarized light means that now there are vibrations in multiple plane. So there are vibrations in multiple plane. So if there are vibrations in multiple plane, for example, if you are going to place your filter like this vertically, right, then only, yes, obviously it will cancel out your horizontal vibrations, but it would still pass your vertical vibrations along the filter. And then when you're going to rotate it and place it horizontally this time, and for this horizontal case again, obviously your vertical vibrations are cancelled out, but horizontal planes are able to pass out. So at the end of the day, the intensity will not have any change, right? Over here only vertical planes are traveling, vertical planes, and over here only horizontal planes are traveling. So at the end, there are some planes actually traveling throughout the filter, right? Even after the rotation, it's not like the entire plane is getting cancelled out. So there are some plane, so there will be no change in rotation. But if this entire experiment was carried out on a plane polarized light, then rotating that filter by 90 degree will create zero intensity. But over here it will not be zero intensity, there will be no change in intensity, because we were working with filament lamp with unpolarized light. So in that case, option C is your correct answer. The intensity does not change over here. Moving on to properties of waves. Now in this question it says that when laser is shown through a diffraction grating, a series of maxima is formed on a screen. If you guys remember diffraction grating, they have a formula of it was n lambda is equals to, wait 1 minute, lambda is equals to nd sine theta. So yeah, n lambda is equals to d sine theta. This was the formula. Now over here it says that assuming all factors remain constant, which of the following changes would increase when the distance between the adjacent maxima and minima? Okay, the distance between the adjacent maxima and minima is basically not the small d over here. This small d actually indicates that the distance between each lining on the diffraction gratings filter, and the distance that we are actually talking about is on the screen on the opposite side. Okay. On the screen of the opposite side, this is for n1, this is for n0, which we would actually consider as x over here. The distance between two adjacent maxima is considered as x, and they're saying that the value for x is supposed to increase. Another thing to remember, this is your screen, like this is where your screen will be, and this is your diffraction grating filter. The distance in between them, this capital D, this is capital D over here, we can actually calculate theta from these two values, right? X and capital D. X was the distance between the maxima, and D was the distance from the diffraction grating to the screen. So we can calculate that using tan theta. So tan theta is equals to x over D. Now, in order to have an increased x, in order to have an increased distance between two adjacent maxima, the value for the angle must increase over here, right? The one thing that must increase is a value for the angle increase. I just make x the subject of this, then it will be easier for you to understand. Tan theta, right? So we can understand that the distance between adjacent maxima is directly proportional to the distance between the screen and the diffraction grating filter, and it is also directly proportional to your theta, right? Theta over here, the angle of deviation. Now over here, they both might increase, and their increase in both cases will cause an increase in the value for the distance between the adjacent maxima. So according to that, if I go to this decreasing the distance between diffraction grating and the screen. No, decreasing the distance between the diffraction grating and screen, that means decreasing this capital D. This capital D, like decreasing this capital D will obviously cause a decrease in the distance between the adjacent maxima. So this is completely wrong. This is the opposite of the correct answer. And then they're saying that decreasing the distance between the lines on the diffraction grating. Now over here, focus on this. This is not, they're talking about the distance from the filter to the screen. They're talking about decreasing this distance. How can this distance be related to this situation? This distance has to be related to theta, and then again theta has to be related to x over here. So let's identify how this small d, distance between the lines on the diffraction grating filter, how that is related to your theta. So if I make d the subject, that is going to be n lambda divided by sine theta. Now I can clearly understand that they are inversely proportional, right? Angle and your distance between the lines on your filter are inversely proportional. So if they are inversely proportional, if they are inversely proportional, that means decreasing the lines between decreasing the distance between the lines on your filter will cause a higher value for theta, higher value for deviation. And if theta increases, and theta and the distance between adjacent maxima were directly proportional, so if theta increases, this one would also increase, right? So in this situation, they're not actually using this relationship, they're using this relationship, that d is equal to n lambda over sine theta. If d decreases, theta increase, because they are inversely proportional, and then again theta is directly proportional to x. If theta increases, this one decreases and this one increases, that means if theta again increases, the value for your distance between the adjacent maxima will also increase. And depending on that, option B is your correct answer over here, right? Other than that, intensity, decreasing wavelength, they do not have anything related to this concept over here. Okay, this was it. Then moving on to the next question, which may be the longitudinal, so waves may be longitudinal or transverse. Which of the following statements is correct over here? All transverse waves travel at the same speed. Which of the following statements is correct? All transverse waves travel at the same speed. All transverse wave vibrations that are parallel to the direction of wave travel. This is completely wrong. This is the definition for a longitudinal wave. Both transverse and longitudinal waves can be reflected. No transverse wave can pass through liquids. This is again wrong, right? Not, transverse wave can pass through liquids. That is wrong. It is not the case that it cannot travel through liquids. And I'm actually, wait 1 minute. Both transverse and longitudinal waves can be refracted. Oh, sorry, sound waves cannot be refracted actually, right? They could be reflected, they could be diffracted, but they're not refracted. So this is also not correct. In that case, option A is your correct answer over here, right? All transverse wave travel at the same speed, which is actually 3 into 10 to the power of 8 meters per second, the speed of light. Right, so this is your final answer for question 8. And then again for the next part, in an experiment, laser light is shown through a diffraction grating so that a series of bright dots appear on a screen, and the equation n lambda d sine theta can be used to determine the wavelength of the laser light. Which of the following is correct description of how the experiment should be performed? The angle is measured using a protector. Now you can never measure the angle with a protector because this is entirely happening in air, right? This entire thing is happening in air. So how can you hold that protector in air? So over here what you have to do is that you're going to measure the value for the distance between the two adjacent maxima and the distance from the screen to the filter, and using that equation tan theta is equals to x over d, you can find out the angle, right? So obviously we do not use protector over here. Instead we use the equation tan theta x divided by capital D. And then again the diffraction grating is set up so that it is parallel to the laser light beam. No, it is not parallel to the laser light beam. The diffraction grating is like this, and the beam must travel in this direction. It is actually perpendicular to the laser light beam. The diffraction grating filter should be parallel to the screen but perpendicular to the laser light. So the correct answer over here would be if the wording was perpendicular instead of parallel. So this is again wrong. The diffraction grating is set up so that it is parallel to the screen. Now this is correct, right? This is your filter and this is your screen. So obviously they both needs to be parallel to each other. After that, the distance between the bright dots is measured using a micrometer. Again wrong, we cannot obviously measure that using a micrometer. Micrometer are only used to measure a three-dimensional object, right? We can use a meter ruler over here to measure the distance between that two adjacent maximas that are going to be created on the screen. So we can write meter ruler. Okay. Now, after this, we'll move on to the next question. The evidence of the wave nature of electrons come from the experiments involving diffraction, polarization, reflection, and refraction. Now, over here, polarization can only occur for lights or for waves that travel in multiple directions. So, this cannot be used for the evidence of wave nature of electron. Okay, this is only for waves traveling in multiple directions. Multiple planes. And then again reflection, electrons cannot be reflected, so no. And then again refraction cannot be shown in reflection in electrons also. But if you remember, if you guys have chemistry also, you would have seen this I think that was electro wait I think it was like electron crystallization or something, where we can actually see the shape of your electron shells, right? That is yeah. I remember it was electron diffraction. I mean electron crystallization basically, but in in chemistry you would refer to that situation as, or that entire phenomenon as, electron crystallization. And in electron crystallization, we obviously do not freeze the electron. We are going to pass the electron through some photoelectric material, and we're going to create an image of that, and that image will show that electrons can be diffracted, right? So diffraction is your wave nature of electron. So this is your first answer, wave nature of electron. And then again, if you would have to find out the particle nature of wave, that would be photoelectric effect, right? Wave nature of electron is diffraction, and particle nature of wave is photoelectric effect. Let me just write this down as a wave, as a notes again. Okay, then again for the next question, it says waves can be represented on graphs of displacement against distance and displacement against time. Which of the following properties can only be determined by combining information from both graphs? Okay, now for displacement against distance from this type of graph, you can get displacement, I mean, you can get amplitude, you can get what else, you can get a wavelength. Okay, so you can get amplitude and you can get wavelength. But from displacement and time, okay, from this type of graph you can get, again, amplitude is possible to be required to be like to be measured from this type of graph. And now you can find out time period from this. Using this time period you can also find out frequency from this, right? So which of the following properties can only be determining by combining information both graphs? So for both graphs, the only thing that you can get over here is what I mean, amplitude is possible from both, frequency is possible from either with displacement time, and wavelength is only from displacement distance. That means from both you have to you take displacement from wavelength from displacement distance and time period from displacement time. So speed is the only quantity that requires information from both the graphs. So this is from both graphs, like you can get that on both the graph, right? But then again, this one is only available for displacement time graph. This one is available for displacement distance graph, right? And you need to use both graphs to calculate this speed, which is v is equals to f lambda. So D over here is the correct answer. Okay, this is again a very, I would say, repetitive question, because you need to understand that for displacement distance graph, you're never going to get time period from there. You're only going to get lambda or amplitude from there, right? And from displacement time graph, you cannot calculate or measure wavelength from there. You can only get time period, and using the time period, you can find out the frequency using that formula f equals to 1 over t. Okay, this again, I'll just write the repeated pattern over here. After this, let's move on to this question. It says that a diffraction grating has 300 lines per millimeter. Okay, this one, 300 lines per millimeter. When laser light is directed towards the diffraction grating, a diffraction pattern is observed on a screen, and the position of a first order maximum on the screen is shown in the diagram. Now, this is your N0, this is your N1, and the distance between N0 and N1 is 0.4. This is your capital D. This is your X. And for small d, you have to use unitary method this time. But let's just read the question, that which of the following calculations should be used to determine the wavelength in millimeter of the laser light used. Okay, in order to understand this equation, I can clearly understand I'm using n lambda d sine theta. For that, d over here, d was that distance between each adjacent lines on the diffraction grating filter. Now they are saying that on on average there are 300 lines per millimeter. That means in 1 millimeter there are 300 lines. For one line, what would be the final distance then? We can write it like this, that for 1 millimeter they have 300 lines, or it should be the other way around. The 300 lines are actually occupying 1 millimeter space. So that means one line, basically one line, I'm indicating that as the distance between one line, okay, the gap between one line. Okay, so now one line represents that basically the distance between two lines, and this is what that small d represents, and this will be 1 over 300. Sometimes we have to convert this into meters, but as we want to find out the lambda over here in terms of millimeter, so no need to do the conversion over here from millimeter to meter. We got the value for small d, and we can also find out the value for theta. That will be what? This time they are using 2 and 0.4 in all the cases. Yeah, we can find out theta over here. That is what? Tan inverse theta by, like, opposite over adjacent. This is basic trigonometry, right? On the opposite you have x, and on the adjacent you have this capital D. So theta is going to be tan inverse 0.4 over 0.4 over 2.00, and that is the value for theta. Okay, now using this theta and the value for what is the small d, you can find out the value for your n lambda. So that would actually be n lambda is equals to d sine theta, right? N over here is going to be 1 because it was for first order. So basically we're going to get n is equals to sine theta is going to be sine theta divided by 300, right? Because d was 1 by 300, 1 by 300 into sine theta is going to be sine theta by 300. Okay, now then again, where theta is tan inverse 0.4 divided by 2.00. So this is your correct answer in that case, right? Where theta is your tan inverse 0.4 and 2, right? Which is exactly your option C. So option C is your correct answer in this case. This is very important to understand how to find out the value for your small d, distance between the adjacent length on your diffraction grating. That is extremely important to understand that. Okay, so after this, we'll move on to your next part. Question 5. Ultrasound is a number of different has a number of different uses in medicine. Which of the following is the main reason why ultrasound is not used to perform the scans for chest and lungs? The air in the lungs cause most of the ultrasound to be reflected back. The duration of the pulse of ultrasound limits the area of detail that can be seen. The wavelength of the ultrasound is too long. The ultrasound can cause damage to lungs. No, if it ultrasound was actually harmful, then it would create harm. I mean, it would be like harmful for all the parts of your body, right? Not just for lungs. So obviously option D is not correct. I can understand that. And then again, for part C, the wavelength of the ultrasound is too long. If the wavelength was too long, then I would not be using that for other cases, because wavelength actually resembles to like actually relates to resolution for your image that will be created. Okay, so if your wavelength is very big, then the image will be more distorted. Lower resolution image will be created. So I mean, obviously I would not be then using ultrasound for any of the other cases, for scanning any of the other body parts. So let me just write this down. If this is the case, if wavelength is too large, this indicates that lower resolution blurry image. Blurry image, and then again, lower resolution blurry image is only the final result for higher diffraction. Larger wavelength means diffraction would occur inside the body, in between the tissues, which would cause this lower resolution or blurriness of the image. So this is all because of diffraction. Right, and if this was the case, then I would not be using ultrasound for all the other body part scanning. So this is again not the correct answer. For part B, it says the duration of the pulses of ultrasound limits the amount of detail that can be seen. That is again not correct, because if that was the case, again I would not be using this for other parts, right? Duration of the pulses should not be considered as a problem, because duration of the pulses should be very large, right? After releasing the first pulse, I will not release the second pulse until I receive the reflection of the first pulse, right? So the duration between each pulses should be extremely large to prevent mix up of the reflected waves. Okay, that is again not correct. That means the only answer over here is option A, that air in lungs will cause most of the ultrasound to be reflected back. So over here, option A is your correct answer. Right. Now, obviously, to be honest, when I started working this, I had no idea that air would cause higher reflection. I really do not have any idea for that. But I understood the idea by cancelling out the other processes, other formulas, other statements over here. But then again, there's another point related to this. What exactly happens is that when that ultrasound will actually move from your skin to air, there's a drop down in density, right? And whenever there will be a drop down in density, light will be reflected back, right? Because this is how the entire boundary is. This is your skin, and this is your inside the lungs or skin or whatever the material is with which your lungs is made up of, and in between that now you have air, right? In this part you just have air over here. Now again, what happens, skin obviously has a higher density, air has a lower density. So when light needs to travel from, this is high density, I'll just write high density, 1 minute, high density, and this is the air portion is low density. And for that high density, low density, when your light is traveling from higher dense medium to lower dense medium, total internal reflection will occur. And if total internal reflection is occurring, that means this is your ultrasound, this will go back, and from this medium it will travel back. Total internal reflection. It will no way enter inside your lungs, right? Because total internal reflection was occurring in that case. So obviously option A was the correct answer over here. I mean, to be honest, I didn't knew also that option A would be the answer, but somehow it got into my mind. I hope it gets into your mind also tomorrow in your exams. Okay, other than that, nothing else. We'll move on. I would suggest very, very important question for this. Like I thought it was quite tricky and has a lot of depths and folds in this question, even though it was just for 1 mark. Let's move on to the next one. Ultrasound can be used to investigate organs inside the human body. Which of the following segments about ultrasound is correct? All of the ultrasound is reflected at a boundary between different tissues. Ultrasound travels faster in air and then inside the body. Ultrasound with a greater wavelength gives an image with higher resolution, which I can clearly understand is wrong. Right, ultrasound with a greater wavelength will cause diffraction, will create lower resolution. We just saw that in the previous question. So obviously part C is wrong, and ultrasound with a shorter pulse duration gives an image with higher resolution. This one's correct. Over here, answer D is your correct answer. Shorter pulse duration. That means that shorter pulse duration means that it will take short time to get reflected from the surface, right? If it has a shorter pulse duration, then I can release a second pulse very quickly. So option D over here is your correct answer. All the other parts are wrong. Ultrasound travels faster in air than in body. We do not know that, or basically AMF actually travels with a speed of 3 into 10 to the power of 8 in all cases, right? So this is wrong, and in all mediums, so this is wrong. And all of the ultrasound is reflected at a boundary between different tissues. This is not again a correct answer because we will apply a gel on top of that. Like no, actually, I mean they're talking about different tissues. That means that they are talking about inside the body. For inside the body, different tissues will not be a bigger matter because ultrasound have very, very small wavelength. For that small wavelength, I mean, the distance between the tissues will be, very large compared to the wavelength of the ultrasound. If the wavelength of the ultrasound is very small compared to the distance between the tissue, then it will not create diffraction. If there will be no diffraction, in that case, it will not be reflected in between the tissues, right? It will not create multiple reflections. So, no, that is again not the case. Option D is your only correct answer. Okay, moving to part 4. Electromagnetic radiation can be described in terms of a photon model. Which of the following demonstrates the photon model of light? This is the one we wrote at the very top of some question maybe. At the wave nature of electron, we write diffraction, and the photon model of light is photoelectric effect, right? So this is your option, right? Diffraction pattern, Huygens construction, plane polarization, they are not indicating about the photon model of light. Only photoelectric effect indicates about photon model. So let me just write this down again. Diffraction indicates spreading out. Huygens principle indicate that every source on a wave, so every point on a wave can create a new wave. So I just write like formation of wave. Okay. And then again, photoelectric effect is the final answer, and plane polarization is just indicates that they have multiple planes in which they're going to vibrate. The light over here actually vibrate in multiple planes. That's what we understand using the polarization process. So multiple planes. I'll just write multiple planes. Okay, then again, a graph of displacement again times for a point on a transverse progressive wave as shown. Which of the following statement is correct? The amplitude of the wave is 2, which is not correct. Amplitude is 10. Right, this is the maximum displacement, amplitude is 10, and the frequency of the wave is 2 2.5 hertz. I do not know, let me just measure. From one crest to another crest, this is 0.4. So time period is 0.4. In that case, frequency would be 1 divided by 0.4 is, 1 divided by 0.4 is 2.5, right? Let me do the working. This is 0.4, this one 0.4. In that case, frequency is 1 divided by 0.4. This is 2.5 hertz, which indicates option B is your correct answer. Other than that, nothing else is obviously we're going to focus on. We obviously cannot get wavelength because this was displacement against time. Very important to understand, very important to focus on the graph's axis. Whenever they're going to provide you a graph for waves, you always focus on the x-axis. Y-axis will remain displacement, but for the x-axis, it will have time or it will have distance. For time, you cannot get wavelength from that graph, right? This is a displacement against time graph. From this graph, you can never get wavelength. You can never get distance because on your x-axis you have time. How can you get wavelength from there? So obviously option D is wrong. and the period of the wave is 0.2, which is again wrong. This is not for one period, this is half of the period. For one period, we are going to measure that from one crest to another crest, that is 0.4. Okay, this is it for question 7. Then we'll move on to the next one. A ray of light travels through the glass towards a boundary between glass and air. The critical angle for this boundary was 42. Which row of the table is correct? Angle of incidence, what happens at the boundary? Okay, over here the critical angle is 42 degree, and the ray of light travels through glass towards a boundary between air and glass. Okay, it says that at 40 degree. Okay, remember that at 40 degree, the angle of incidence is less than critical angle. That means total internal reflection cannot occur, right? But whenever we are working with 45 degree, now they have angle of incidence greater than critical angle, and now total internal reflection could occur. So for 40 degree, light is refracted, all of the light is reflected. This is wrong, right? All of the light is not refracted, reflected, and again at 40 degree, not all of the light will be refracted. At 40 degree, partial reflection will occur, partial refraction will occur, and obviously there will be incident ray on your diagram. But and then again at 40 degree, total internal reflection cannot occur. All of the light is reflected, indicates TIR is happening. And this is not the case. It can only occur if your angle of incidence is greater than 45 degree. Sorry, 42 degree critical angle. That means 45 degree, all of the light is reflected. Option D is your correct answer. Okay, then we'll move on to October 2021. A student determines the wavelength of a light emitted by a laser. She uses the laser, a diffraction grating, and a screen. Which of the following statement is not correct? Distance from the diffraction grating to the screen. Wait, what? The student determines the wavelength of the light emitted. Oh, what is not required over here? The distance from the diffraction grating to the screen, the distance from the central maxima to the first order, the distance from the laser to the diffraction grating, the distance between the slits in the diffraction grating. Okay, 1 minute. The student determines the wavelength. She uses a laser and diffraction grating on a screen. The distance between the distance from the diffraction grating to the screen. Okay, the distance between the central maxima to the first order, the distance from the laser to the this one. This is not required. From the laser to the diffraction grating, we do not need that. This is your capital D. This is your small x, and this is your the distance between the slits. Yeah, this is your small d. But all of the things are required because in your equation, n lambda is equals to d sine tan inverse theta is basically tan inverse x over d, right? So all of these things are required. Capital D, small d, x, these are required data, but only the distance from the laser to the diffraction grating filter is not required over here. So obviously we are going to choose option C as your correct answer. Like invalid invalid requirement for this data. Okay, now for this Jan 22, this is quite small. The diagram shows refraction of a ray of a light as it passes through the three transparent substances L, M, N. The speeds of the light in the three substances are V1, VM, VL, VM, and VN respectively. Which of the following shows a relationship between VL, VM, VN? Okay, now we can clearly understand. Let's first draw our normal over here in order for a better understanding. Okay, now always remember in higher dense medium, your waves will be actually, refracted towards the normal, and in low dense medium, it will be refracted away from the medium. Okay, so let me just write this down as a notes that during refraction in low dense medium, Okay, so this is the procedure that in high dense medium, so in low dense medium, your waves move closer to the normal, moves away from the normal, and in high dense medium they move close to the normal. Now in this case you can understand, if you can measure the theta, or approximately you can identify where the theta will be greatest or where the theta will be smallest. We can understand that at the M medium or the middle medium, the angle was very small, right? If the angle was very small, that means obviously this is very high dense medium. This is high dense medium. Okay, this is high. And in comparison with L and M, L has a like N has a smaller angle compared to L. So this is a moderate medium, and this is a low dense medium. Okay, this one, because at L the angle it was creating with the normal was very high, and using this angle I can understand that then density for L was lowest, N was moderate, and M was maximum. And again, what happens in higher dense medium, velocity is very small because it has higher resistance, so it would need more time to travel the distance, so velocity drops down. So the higher the dense, the smaller the velocity. Okay, then one thing we can also add from this part is density and speed is inversely proportional, right? So density is inversely proportional to the velocity of light. Now in this case I can understand that if this is from L, N, M, in that case your answer should be that lowest at L, moderate at N, and maximum at M. So in that case, L, N, M, option B is your correct answer, right? Right, option B is your correct answer. So yeah, and this is it for your working for part, this question 5. We'll move on to the next question. Which of the following could result in a ray of light undergoing total internal reflection? Okay. For total internal reflection, obviously that light must pass from high dense medium to low dense medium, right? So in that case, from M to L or M to N, both can create uh, total internal reflection. Light traveling from M to L, right? This is your answer, M to L, from high dense medium to low dense medium. So option C is your correct answer. I should write this down. High dense medium to low dense medium. Okay. Now it says a ray of light is incident on the boundary between two materials X and Y as shown. The refractive index value for the material X is small n1, or it is nx. Sorry, nx. I cannot see this on the entire file because it's so small. Okay, x is nx and the material for y is ny, and the angle of incidence is given. Which of the table gives the conditions required for total interreflection to occur at this boundary? Okay, I obviously must be greater than critical angle, and then again density of x should be greater than density of y, right? That is the condition. So I greater than critical angle, so between A and B, your greater than, option A is your correct answer, right? Density of x is greater than density of y, and this must be greater than critical angle, right? Option A is your correct answer. This is again quite of a repeated question, I would say. Memorize this question because it has both the conditions fulfilled for total interreflection, angle greater than critical angle, and your density for x greater than density for y. This question, the graph shows how the displacement x of particles in a wave varies with time t. The speed of the wave is not shown, and which of the following can not be determined from a graph of displacement against time for the particles in a wave? Okay, amplitude, frequency, period, they all can be calculated. Only wavelength cannot be calculated over here. So option D is the correct answer. Moving on, a ray of light is incident on the glass block as shown. Which of the following does not occur when the ray of light is incident on the glass block? Reflection occurs, refraction occurs, reflected A is polarized ray. So B, C, D, they all are going to occur in this kind of changes. Only diffraction cannot occur because light is not traveling through a gap over here, right? So yeah, this is all the correct answer. Always remember from this thing to understand that reflected ray is actually polarized ray. So that means obviously polarization is also occurring for this kind of diagram, right? Okay, ultrasound scan can be used to create an image of the patient's kidneys. For each ultrasound pulse sent into the body, a number of pulses are detected. Which of the following explains why a number of pulses are detected? Interference occurs when the pulse is in the body. The ultrasound reflects of different layers within the body. The ultrasound has a very high frequency. Ultrasound has a very large wavelength. Obviously, this is not the correct answer. Other than that, wait 1 minute. Interference occurs when the pulse is in the body. I mean, interference can occur when the pulse is in the body, but which of the following explains why a number of pulses are detected? I mean, why can you detect number of pulses? That means obviously the pulses are getting reflected from the surface of your body, right? From the different layers inside your body. So option B is your correct answer over here. That ultrasound reflects of different layers within the body. Then again, this is a transducer solid object and that is 10 centimeter length. It says an ultrasound transducer is placed on the surface of a solid object as shown. A pulse of ultrasound is transmitted into the object. The pulse is received at the transducer 50 microsecond after it is emitted. Which of the following can be used to calculate the speed of sound in this object? Obviously, this is a pulse echo technique. For always echo, the speed, I mean over here, the light actually travels or the ultrasound actually travels twice the distance. So that means it is going to be V is equals to, sorry, this is for pulse echo technique. V is equals to twice dt. In order to find out V, this is going to be twice 10 centimeters, right? So it's going to be 10 meter, which is 0.10. 2 into 0.10 divided by time was 50 microsecond. Micro means 10 to the power of 6. I would suggest memorize these prefixes: 10 to the power of 6, 10 to the power of minus 6, then mega 10 to the power of positive 6, kilo 10 to the power of 3, pico 10 to the power of 12, then nano 10 to the power of minus 12, minus 9, right? These are very important to understand or memorize. 15 to 10 to the power of minus 6. In that case, yeah, I can simplify this, and that will be 0.10 divided by 25 into 10 to the power of minus 6. 25 into option C is your correct, option B is your correct answer then, right? Yeah, this is the final answer then, option B. I hope this was clear enough for all of you to understand. Let's quickly move on to your next theoretical question. Now over here it says that state the conditions required for total internal reflection to occur. We have seen this right before in the MCQ section, that angle of incidence must be greater than critical angle and light must travel from a higher dense medium to a lower dense medium, right? So we're going to write the equations. This is very much repeated question. RQ light must travel from optically more dense medium to an optically should be greater than critical angle. Okay, this is the final answer. Then a ray of light is incident at the end of the glass fiber and it refracts as it enters the glass. Explain why the light refracts as it enters the glass. It could happen because wait, a ray of light is incident at on the end of the glass fiber and it refracts as it enters the glass. Explain why the light refracts as it enters the glass. That is because whenever it's going to enter inside the glass, there will be a change in medium. It will move from low dense medium to high dense medium. In high dense medium, it will have a lower speed, at a lower speed, it will have a lower wavelength, and because of a change in wavelength, it will change its overall wave direction, which will cause the refraction to occur. So we can write it like this, that due to high dense medium, wave slow down, so wavelength decreases, and therefore the direction also changes. So wavelength decreases, changing the direction. Right, and this change in direction is referred to that overall refraction, right? So this is the final answer. One thing to remember over here is that in refraction, frequency never changes. Okay, frequency will always remain the same. So frequency remains same in refraction. This is a very important to memorize or understand. Again, this is a part of notes, so I'll just write it like this. Okay. After this, we have a few calculation that is basically using trigonometry, not that much excessive trigonometry, basic trigonometry. They want you to determine the value for theta between emerging the ray and the normal. Okay, glass of refractive index is 1.5 and a wave, sorry, water refractive index is 1.3. This is 90 degree. I mean, if the value for C was given to you at some point, we could have used that. Oh, wait, 1 minute. This was total internal reflection occurring, right? That means the angle for C is going to be equal for the angle for this one also, right? Whatever the angle it was creating in that point, that will be equal for this part. Wait, 1 minute. I mean, over here I can also understand that this C is greater than critical angle. This is greater than critical angle, so I can use critical angle to, wait, 1 minute. Let me just write down, read the question. The diagram shows a ray of light being totally internally reflected at one side of the glass fiber and then refracted as it leads to the end of the fiber. The angle of incidence at the boundary between the glass fiber and the air is equal to the angle C for the, wait, the angle of incidence at the boundary between the glass fiber and air is equal to the critical angle for the glass air interference. The ray enters water as it leaves the glass fiber. Okay. Mm, the angle of incidence as at the boundary between air fiber and air, so glass fiber and air, is equal to the critical angle. Over here, this indicates that your angle of incidence is equal to the critical angle this time. So if it is equal to the critical angle, I can understand I have to use your equation of like critical angles equation. Sine C is equals to 1 over n. This time I'm going to use the n as the value for your refractive index of glass, because now your object was moving from glass to air, right? At this point, from glass to air. So let's just work out for this first air glass boundary or glass air boundary. This is actually glass water, and on that total interreflection session, your entire ray was interacting with glass air boundary, right? So this is just glass air boundary. So during that, or at position for glass air boundary, your object was actually creating a critical angle. So your object was actually creating an angle of incidence which was equal to the critical angle also. So we can write in, sorry, in glass, sorry, in glass, sine angle I is equals to n air sine angle R. This time, if it is creating angle R, that means I already know angle R is sine 90, which is going to be 0. So, which is going to be 1 over here, right? So, it was already stated that angle I is equals to angle C. So now I can write n in G was actually 1.50 multiplied with sine angle C. Sorry. Um, refractive index of air was 1 multiplied with sine 90, which is going to be C. Angle C is actually going to be sine 90 multiplied with 1 divided by 1.5, and this entire thing will be inside a sine inverse function because it was angle sine angle C, right? So for that it will be sine inverse function. And using this you can calculate the value for your critical angle or angle of incidence, which is going to be 41 0.8 degree. Okay, now go back to your diagram again. If this is 41.8 degree, now again how can that be 41.8 degree? Because obviously angle of incidence is also equal to angle of reflection for total internal reflection to occur, right? So this one would also be 41.8 degree. If this is 41.8 degree, I can extend it and consider this is 90 degree. I can calculate this value also, right? The angle of incidence for the glass water boundary. So let's just first find out the total. I mean, let's just first write this, that angle of reflection is also going to be 41.8 degree. No need to write anything, or you can write in something over here, that angle I is equals to angle R. After that, we're going to do our calculation for angle of incidence for glass water boundary. For that glass water boundary angle of incidence, we are going to use trigonometry, 180 minus 90 minus 41.8. So angle of incidence is 180 minus 90 minus 41.8 degrees, sum of a triangle basically, and you're going to get 48.2 degree. So if the angle of incidence is 41.2 degree, now you can use your sin I over sin R to calculate the value for R. Theta over here was the refractive angle. So this will be, it was actually traveling from glass to water, right? So this is going to be in glass sine I, in water sine R. And sine, like diffractive index for water is no longer 1. So in order to find out the value for R, this is going to be, in G was 1.5 into sine I was 48.2 degree divided by in water, refractive index of water was 1.30, and this entire thing will be inside the function of a sine inverse. And if you calculate that directly, this should give you approximately 59.3 degree, and that is the value for your theta over here. I hope this was quite clear. These kind of questions are very common in your calculations, so I would suggest practice these a few. So we'll move on to the next question. Okay, it says the trails of a railway track are usually made from a steel which can withstand the high stress of a heavy materials, through heavy trends. However, steel can develop cracks over time, leading to accidents if not repaired. Large cracks on a rail, such as the one shown in the photograph, can easily be observed, and ultrasound too is commonly used to detect cracks that are too small to be seen. A ultrasound transducer transmits a pulse of ultrasound at the top of the trail and records the time taken for the pulse to return. If the time is less than the time expected for the pulse to return from the bottom of the rail, a crack is present. Okay, state why an ultrasound pulse would be reflected by a crack in a rail. Because there will be a change in boundary, like pulse reflects at the boundary between the different mediums. That's why we're going to get a reflection from that part, because ultrasound is supposed to travel through the material, through the steel, but whenever there's a crack, it will be a change in medium from steel to air, because crack has air, right? So between that steel to air, obviously there will be a drop down in density, and light, I mean, or ultrasound over here will certainly be reflected from that steel boundary, because of light being like ultrasound being traveling from high dense medium to low dense medium. It matches with your first criteria for total internal reflection. So the first answer over here is that pulse reflects at the boundary between different densities. Okay. Now after this, you have this diagram. Estimated pulse is this, and this is reflected pulse. Determine whether the reflected pulse is from a crack in a rail or from the bottom of the rail. Depth of the rail is 15 and speed of the ultrasound in steel is 5800. Okay. Mm, okay, let's just find out that how much time was there in between the transmitted pulse and in between the reflected pulse. So the time between the transmitted pulse and reflected pulse were measured in microsecond. So microsecond. This is approximately what? 5.678. Yeah, this is 6.5, and from the end to end, this is again 31.5. Yeah, 31.5. So the difference would be, this is 31.5. So difference is 31.5 minus 6.5 is 25 microsecond. And then again, time over here between the reflected and transmitted pulse is 25 microsecond. Using this 25 microsecond, um, 1 minute. If this is the transmitted pulse and this is when the reflected pulse was taken, that means obviously time will be half of that, right? Because in reflection, it travels twice the distance. So this the total time actually will be, let's just find out the time over here. Let's just write the time that we calculated first. Time from transmitted to reflected, that is 31.5 minus 6.5 is equals to 25 microsecond. And that means half of this time will be taken for that reflection, because always remember, in pulse echo technique, it travels twice the distance, right? So time is actually going to be, actual time over here is going to be half of 25, that is what, 12.5 microsecond. And using this time and velocity, you can find out the distance, right? So distance is going to be 12.5 into 10 to the power of minus 6 into 5800, that is 12.5 10 to the power of minus 6 into 5800, that is 0.0725 meter. Okay, 0.073 meter approximately. Now this is not, this is approximately what, plus, so if you multiply this with 100, this is 7.3 centimeters. This is not 15 centimeter. The actual depth of that rail was 15 centimeter, and this is, then this entire ultrasound was only reflected from a depth of 7 centimeters from the top surface. That means obviously they have a crack over here, right? It never reached that bottom of the rail. It reached that crack. There is a crack. So we can see that, so reflection is from a crack and it never reached the bottom of the rail. Is from a crack. Okay, then after this was it for all the working. Then we'll move on. Suggest why this ultrasound method may not detect multiple cracks in a piece of rail, because if there are multiple cracks, most of the ultrasound will be reflected by the first crack, and they will, like, not most of, like, not entirely of it will reach to the second crack or cracks beneath that, right? So cracks in a deeper, in deeper sections cannot be detected using ultrasound. So we can write most of the ultrasound will be reflected by the first crack. Most of the ultrasound is reflected by first crack. Okay. To detect cracks, transducers are attached to the wheels of special trains. Explain why these trains must travel much more slowly than passenger trains, because they need a time duration for that reflect, like to receive the reflected pulses also. right? If they're going to travel at a very higher speed, they certainly cannot receive the reflected ultrasounds from the rails. So there has to be a time delay before they can receive their signals. And yeah, I mean, yeah, that is only one case, but they're only giving 2 marks for this. Yeah, I mean, yeah, that the same point over here is actually, to be honest, like there is nothing else other than that. If it is traveling at a very high speed, it will no longer be at the same stage, so it will not be there to receive the reflected, like reflected ultrasound from the rail surface, from the rail cracks. So we can write that if it is moving too fast, it will not not stay in the same position. So there must be a time, and there has to be and there is a time delay for the reflection to occur, right? So the train must travel at a lower speed to remain in the same position. So if it is traveling at a higher speed, then it will no longer stay at the same position to receive, and there is a time delay, but there is a time delay for the reflected ultrasounds to go back for reflection. Okay, this was it. Now this is another diagram state what is meant by plane polarization. This is again extremely important, repeated question. Vibrations in one plane and vibrations in multiple plane. Wait 1 minute. What is meant by plane polarization? Okay, plane polarization means that uh, wave that only vibrates in one plane, that is direction, vibrates in one plane that is parallel to the direction of wave travel, right? Now that is the final answer over here. So we can write that waves vibrating in one plane that is parallel to the direction of wave travel. Okay, again a repeated question that was, deduce whether the refracted ray is unpolarized or partially polarized. Okay, I don't think I can wait 1 minute. Yeah, I mean for that part, I think we need some mathematical calculation which I didn't include it over here because this was just specific for your equation for this kind of question. So I will be actually skipping this. And again for this part, it says that different colors of visible light are refracted as they pass through a prism as shown, and it's this is the entire dispersion effect basically. A student suggests that the Brewster angle for violet light would be smaller than that for the red light, as violet is refracted more than red. Criticize the suggestion. Okay. Violet is obviously bending at a higher angle than red, and they say that Brewster angle for violet light would be smaller than for red, as violet is refracted more than red. And I think this is again related to some calculations we did for the previous parts for B, but I think we can calculate that again. I mean, refractive index for glass over here is greater than air, obviously. And other than that, you have to think of it like this, that higher the angle of deviation, this means higher the um, no, not sorry, yeah, higher the angle of deviation, That means higher the wavelength, right? Something about wavelength was related to this. If I remember VIBG or frequency decreases. No, I can't remember it. Okay, I remember why I kept this in this question in this file. That is, red has the maximum wavelength and violet has the smallest wavelength. Okay, you do not need to memorize this individual wavelength for all the 7 colors. The only thing you need to remember is that red has the maximum wavelength and violet has the minimum wavelength. Okay, now using this information, I can understand that always remember that your lights or waves with maximum wavelength will be refracted less. Okay, so if they're going to be refracted less, that means they're going to be creating a smaller angle, and therefore they will create a smaller refractive index, because now for them the angle of R is small, right? For all of them the angle of incidence is going to be same, but if you remember NG in sine I, this is basically what? Glass to air medium. So Ng sine I is equals to Na sine R. Na is again just refractive index of air, which is 1. So Ng is basically sine R divided by sine I. In this case, I is a constant. They're all going to be they're all going to have the same angle of incidence. So I is same for all the 7 colors. But your color with the maximum wavelength, which is red, will refract less, so it will create a smaller angle of refraction. If it is going to create a smaller angle of refraction, then your refractive index for that color is going to be small. But if you're comparing that for violet, which has a minimum wavelength, so it will be refracted more, it will create a larger angle, therefore it will have a larger refractive index for glass. Right, this is the entire walkthrough for this. I will write the answer, but let me just write down that flow chart first. For red, what was that? It has maximum wavelength. For maximum wavelength, you're going to have small reflection. Small refraction. If you're going to have small refraction, then small theta or small angle r refraction, small angle of refraction. If small angle of refraction, then according to your equation, n is equals to sine r over sine I, because this time they are traveling from glass to air, not from air to glass. This refractive index of glass should be smaller for red, so Ng is small for red color, and this will be the opposite for the violet, right? So I'll write the violet in statements that refractive index is greater of glass is greater for violet, as it is refracted at a greater angle because it has the minimum wavelength. So we can write the refractive index. This is the final answer, by the way. Refractive index, you can write this answer in terms of red or in terms of violet, no problem with that. Refractive index of glass is greater for violet as it creates as it has minimum lambda, as it has minimum wavelength, and refractive index of glass is greater for violet as it has minimum wavelength for lambda, which creates larger angle minimum wavelength for lambda, so it refracts more creating larger angle, or just refracts more is enough, to be honest, right? That is your final answer for this. That's why I wrote this in this question. Okay, after this it says that describe how a value for the speed of sound in air can be determined. This is again a repetitive question, very much common questions, and I would suggest memorize this type of questions, right? Repetitive questions, this is. Okay, when the loudspeaker is switched on, 2 traces are produced on the oscilloscope, one directly from the signal generator and the other from the microphone. Okay, now over here, this is actually your core practical 6 maybe, right? Yeah, this is the description part of your core practical 6. This is also related to unit 3 and unit 2. Now over here, what happens is that initially, at the initial position, obviously there are two traces that are in antiphase or in phase connection. So we need to position the microphone in such a way so that from the meter ruler, so that they are in the two traces from the loudspeaker and the microphone are in phase, and then again move the microphone gradually to the next position when they're again in antiphase or when they're again in phase. And between these two positions, at first point when the sound from the microphone or trace from the microphone was in phase with the trace from the direct signal generator, to that point to the second position when they're again in phase, that will give you one complete wavelength. And obviously we were moving the position for the microphone with respect to a meter ruler. We were measuring that difference in microphone using this meter ruler, right? So the meter ruler will now give you the value for your lambda. Using this, you have measured the value for your one complete wavelength. And now you have value for one complete wavelength. Whatever the sound that we're using, that will be your frequency density. Sorry, on your screen for the cathode ray oscilloscope, you can take reading for time. And using that time period, you can find out that frequency also f is equals to 1 over t. Using that frequency and lambda, now you can use the equation v is equals to f lambda to calculate the value for your speed of sound in air. Okay, this is the entire procedure. So we're going to start with this. Mark the initial position. Mark the initial position when the two traces from the microphone and signal generator are in phase. Mark the initial position when the two. Sorry. Change the position of microphone until the traces are in phase again. Okay, change the position of the microphone until the traces are in phase again. And during these two positions, okay, the distance between these two positions is known as one complete wavelength. Using the meter ruler reading, measure the distance between these two positions. Using the meter ruler reading, measure the distance between the two positions to using the meter ruler reading, measure the distance between these two positions to measure lambda, to get wavelength for one complete wave, and using the cathode ray oscilloscope screen, you can measure time. I'll just write cathode ray oscilloscope, CRO, okay? But you cannot write that on your exam paper. You have to write this in terms of words. Using the cathode ray oscilloscope, measure time period. Then using F equals to 1 over capital T, calculate frequency. Finally, using the equation V is equals to F lambda Calculate speed of sound in air. Okay, this is again a very important repetitive question. I would suggest memorize every part of this answer. Okay, this could also be an answer for a possible star mark 6 marker question. So yeah, this is very important. We'll move on to the next part. Deduce how the cathode ray deduce how the oscilloscope display can be used to demonstrate that the two traces have the same frequencies. We can take that, I mean, if they have the same frequencies, then obviously the time period for the oscilloscope for both the points when they are in phase should be same, right? That is the only case. And if time for both traces are same, that means obviously frequency should also be same. That is the only possible answer over here. So we can write that time period, like we should take reading from the time period for the oscilloscope for that one point to the next point, like from that like between the 2 points when the waves were in phase, and if the time period is same for both the phases, then they are in phase or they have the same frequency. So we can write that take readings from oscilloscope between the points when they were in phase for time period. Take readings from oscilloscope for time period between the points when they were in phase and use, if the time period is same for both, then frequency is same. Okay, now this is a star mark question from January 2021. This indicates that explain how the ultrasound scan of the unborn baby is produced. Okay, now over here there are, I mean, this is again a very repetitive question. I think we did this in some kind of like in GC question paper. There was some entire paper where they would ask this question in this kind of pattern, like they asked it as a normal question, and in your January 2021 they asked you as a star mark question. Okay, so now over here what happens, obviously there are different layers of this answer. At the first layer, the light, I mean that ultrasound must travel into the skin, right? So for that we will apply a gel on top of that skin. This gel will reduce the wait, sorry. As I was saying, this gel will reduce your difference in densities between the air and skin. So therefore, the less ultrasound will be reflected from the boundary of air skin medium. Now, most of the ultrasound can enter inside the skin, right? Inside the body. Okay. Now, when it enters inside the body, we're obviously using ultrasound with the smallest wavelength, so that the wavelength of the ultrasound is very small compared to the distance between the adjacent tissues. So if they're not same between the adjacent tissues, so it will have lower diffraction. Lower diffraction means a higher resolution image can be obtained. Another thing is that inside the body now, whenever the ultrasound is going to come in contact with the tissue, this time obviously they have difference in densities, and because of the difference in densities, now we do not, I mean, we cannot apply gel on top of the tissues also, right? So for that case, now light will be reflected from the top of the tissues now, and from the top of the tissues, the reflected light will be received by the transducer, and those reflected light will be converted and shown on the screen as image. And then again we're going to we're going to have a large pulse duration, so a small pulse duration time. That means after transmitting a pulse, we will receive the pulse, we will not release the second pulse until we receive the reflection of the first pulse, right? So pulse duration between adjacent pulse should be large, so in order to prevent mixing up of reflections. So this is what everything we're going to write for this question 13. But then again, actually, this is already written for your what that list for 6 markers. I've already uploaded previously today, so I'll not write the answer over here. I'll just go back to that file and read that answers from there. Okay, so just 1 minute. Okay, so this is your other file, the one I was talking about. This is the list for all the 6 marker questions in Unit 2. Now we'll scroll back to just January 2021 because we were in that question. If any one of you doesn't have this question, you can obviously ask, and I will try to send that through anyhow, either in WhatsApp or through Discord. Okay, wait, I think I made a mistake. That was not January 2021. 1 minute. Yeah, this is January 2020. This is the final answer. Let me read the answer from here. At first, obviously, wait, where is my cursor? 1 minute. Okay. At first, ultrasound can be reflected from the skin-air boundary, and due to change in densities, which can be prevented by applying a gel of similar density, right? That gel is entirely applied on top of the skin in order to reduce the difference in densities, to reduce the effects of reflection from the skin boundary. Okay, and then smaller wavelength of ultrasound should be used so that the lambda is very small compared to the gaps between the tissues, which might cause diffraction and reduce the resolution of the scan. And then again, time between each pulse should be long to prevent mixing up of pulses. Also, this time should be measured as it will be used to determine the position of the baby inside the position of the baby using the equation d is equals to vt by u. This is the equation for pulse echo technique, right? I just make distance the subject of this because I want to find out the position of the baby from the surface of the skin, right? So this is the final answer. So I will just copy this and paste it on the other file. This is it. The answer should be same over here. And again, this is the list for all, like in this PDF. I have compiled all the questions from like all the 6 markers from your recent question papers. So I would suggest try to contact me in either WhatsApp or in either, wait 1 minute, what happened, right? Or in either Discord to get these files. Okay, this is it. Then we'll move on. Question 15. A water wave approaches a boundary between deep water and a shallow water and is refracted. The diagram shows how the diffraction of travel of the wave changes. This is deep and this is shallow. We can clearly understand deep water is what? Less dense, as your angle is very, as your wave is very away from the normal, right? So this is less dense and this is more dense. Now explain why the wave is refracted as shown as it enters the deep water into the shallow water. You may add the diagram. Now this is the entire case to the previous one, right? That in deep water it has less density, so um, your entire wave travels at a higher speed, and in deep water it has more density, so wave travels at a lower speed. Due to decrease in speed, their wavelength decreases or wavelength changes, which eventually causes a change in direction, right? So we can write that from deep to shallow water there is change in densities. Sorry, there is change in densities. 1 minute. There is change in densities, and from deep to shallow water there is change in densities, and which causes change in velocity and wavelength. Eventually changing the direction of wave. Okay. Now after this, we'll move on. This question is about, I think, Huygens principle. Explain using Huygens construction how diffraction occurs as waves pass through a gap. This is again a repeated question. Okay. For this part, the answer should be that every point. Wait 1 minute. Huygens principle, how diffraction I mean, yeah, this is the entire answer, that every point on a wave acts as a new source of wave. So that's why when wave passes through a gap, um, it will spread out, creating new wave, right? This is the final answer, that every point on a wave, every point on a wave will act as a new source of wave. It spreads out, causing diffraction. Okay, then next part is about May 2020. This question was a little bit tricky. This in this question you have to connect this with um, reflection and refraction. Yeah, reflection and refraction, right? Okay, now in this question it says that the speed of sound in the speed of sound in seawater varies with depth as shown in figure diagram A. Okay, from this part we have speed on the y-axis and depth on the x-axis. And then again for diagram B, sound approaches to a depth of 900 meter, initially traveling towards the water surface. As the sound approaches a depth of 700 meter, it changes its direction and follows the path shown to the point P in diagram B. Okay, and then it says that explain why the sound follows the path shown in diagram B. Your answer should refer to the refraction and your answer should refer to refraction and diagram A. Okay, now over here what happens that okay, I mean I don't know how should I entirely arrange this answer. 1 minute. Let's think of it like this. Your entire journey is starting from 900, right? So when it is starting from 900 to 700, refer to the speed. This is the speed of 900 and this is the speed at 700. We can clearly see that from 900 to 700, speed increases. Speed increases means what? The density overall drops down, right? So from 900 to 700, speed increases, density of the water surface or water medium drops down as it moves to a lower height, and then again it will move away from the closer this time, right? Moving away from the closer means angle of incidence is now will be greater. At this point, angle of incidence might be, I mean, over here again you can see that exactly at 700 what happens? The entire direction changes, right? That means at 700 total internal reflection is occurring. Since again the last point we said that angle of incidence is now greater, that means angle of incidence is now greater than your critical angle. That's why total internal reflection can occur at point 700 exactly. That's why it changes its direction and start traveling towards the point P. Okay, this is how you're going to write your answer. So let's write the answer first, or write the statement first. We're going to write that when waves rise from 900 meter to 700 meter, their speed increases from diagram A. Okay, and due to this increase in speed, it indicates decrease in density, right? Which indicates decrease in density, which indicates decrease in density. Decrease in density causes your what? Decrease in density causes your waves to move away from the normal. So which indicates decrease in density. So waves will move. Sorry, will move away from normal. So waves will move away from normal, and waves will move away from normal, and angle of incidence is greater, and angle of incidence also incident also increases, thus making it greater than critical angle. Thus making it greater than critical angle. Okay, so if your angle of incidence is greater than critical angle, then this certainly indicates that total internal reflection is occurring at point 700. That's why it was reversing its direction, right? So now we can say, therefore, TIR is occurring. This is occurring, by the way. I'm not sure if you can see this. Occurring at 700. And then again, you cannot write total TIR as total internal reflection. I'm only writing this because I do not have much space over here, right? Okay, so this is the final answer for this. I think this was extremely tricky because the graphs were quite confusing. Yeah, I mean, the first time I attempted this, I was also quite stuck on this question for at least 10 to 15 minutes, to be honest. Okay, so we will move on. Suggest sound that travels in a straight line from the surface to P it takes longer to arrive than sound that travels along the pathway shown in diagram B. It says that when there was no reflection, it would take more time than when there is a reflection. And we need to explain why. Because sorry, wait 1 minute. Sound that travels in a straight line from the source to P takes longer to arrive. Right? It could be that. Wait. Yeah, this is one of the procedures that during reflection speed increases, right? We saw that from 900 to 700 speed increases. So if speed increases, even though they were traveling a larger distance, the reflective pathway was actually a larger distance, but at a higher speed it can travel a largest distance at a smaller time. But if they were traveling in a straight line from 900 to point P in a straight line, they would be traveling a smaller distance with a smaller speed, so time will be much longer to travel that, right? So that is the only possible answer over here, that path in diagram B is a longer distance, but sound waves travel faster when in reflection, so it can travel a larger distance within a short time with a higher speed. That is the final answer, that path in diagram B is longer distance. Path in diagram B is a longer distance. So wait 1 minute. Path in diagram B is a longer distance. 1 minute. Path in diagram B is a longer distance. But during reflection. But during reflection, speed increases. So larger distance can be traveled within a short time. Within short time. Okay. And then again suggest two factors that might cause the speed of sound to vary with the depth of the sea. Okay, two factors could be that obviously temperature causes a change in speed, and pressure, right? That is the two factors, the temperature and pressure. And pressure in the sea. Okay, these are the two factors. Okay, after this is your another question. This is, I think, about refraction, right? Yeah, explain what is meant by refraction. That is what? Change in direction of a ray due to change in speed. right? A change in speed, that is refraction. So we can write change in direction of a ray of light due to change in speed. Okay, and then again there's a small trigonometry. Determine the refractive index of the water in the cup, sorry, not cap. Okay, now it says that hmm, yeah, you can find out this angle very easily, and you can find out this angle also quite easily. If this is 3.7, in that case I'll just use this to 1 minute. Yeah, I can use this length, and if this is 4, then this is 4, right? This is your angle of incidence. This is 4, this is 3.7, and this is 1.8, and this is 3, right? So this is angle of refraction. So in that case, angle of I is going to be tan inverse, opposite is 3.7 over 4, and then angle of R is actually tan inverse 1.8 over 3, right? That is your answer. So this is tan inverse 3.7, sorry, 3.7 over 4, that is 42.8 degree, and this will be tan inverse 1.8 divided by 3, that is 30.69, so I can write 31 degree approximately. Okay, 31.0 degree. Okay, now using this I can find out your refractive index for water, right? So this is how it was: refractive index of air, then sine 42.8 degree, and then refractive index for water, then sine 31 degree, which is going to be refractive index of water. I mean, air is 1, we know that, so no need to write that 1 anymore. We will just write sine 42 by sine 31. So sine 42.8 by sine 31, and that is 1.32, approximately 1.32 refractive index. Okay, then we'll move on to this one. We need to deduce the material used for this gemstone. This is very a common type of question. This might appear in your unit 3, unit 6. This type of try to identify the material kind of question is very, very common. Okay, now it says that in order to identify the material, we used a ray of light and directed it towards the boundary between the air and the gemstone. So what we'll do is that we will find out the refractive index this time, right? Which is sine 50 divided by sine 21. Refractive index of the gemstone. So which is going to be sine 50 over sine 21. That is 2.14. This one, which is very close to wait 1 minute. We have this refractive index, right? Okay, using this refractive index I can find out the speed of that light in the gemstone, because I already know speed of the light in air was 3 into 10 to the power of 8 meters per second, right? So in that case I can use this exact equation and make it equivalent to speed in first medium divide by speed in second medium. Over here second medium was your gemstone, so it will be speed in second medium is 3 into 10 to the power 8 speed of first medium divided by that refractive index, that is 3 into 10 to the power of 8 divided by 2.14, which is approximately 1 2 3 4 5 6 7 8 1.40 2 into 10 to the power of 8. Okay, that is your speed of light in the gemstone, and using this I can understand, wait, 1.4, right? Hmm. Yeah, this is almost 1.4, right? This is 1.4 into 10 to the power 8, right? So I can write this is what? Cubic zirconia, right? I'm not sure if I'm pronouncing it properly, but I think that is the material with which this material should be, or gemstone should be made up of. So this is your material, right? It is not diamond, it is not silicon carbide, it is this cubic zirconia, right? That is the material for this. Hmm. So yeah, this is the answer then. We found out the material, and that is your final statement. So we'll just finally write this down as cubic. What was the spelling? So it's zirconia. Okay. I'm still not sure if I'm pronouncing it correctly or not. Okay, whatever it was. Yeah, this is it for how you'd suggest, or how would you actually identify if a certain material is made up of which kind of material or something. Then again, you have this kind of angles. Add to the diagram to show the path of ray of light as it leaves its boundary. Your answer should include a calculation. Okay, now over here, this is how it will travel. This is going to be a total internal reflection over here. Okay, if this is a total internal reflection, and then after that again, from this part, it will again be total internal reflected, and again from this situation, okay, from this part we're going to have to draw the normal. This is your normal, one normal. We're going to copy this and paste it. This is again your normal. Okay, now we have to write calculations also, right? Why? Okay, add to the diagram to show the pathway as it leaves the boundary. Your answer should include a calculation. Okay, I'm not sure what to calculate over here, to be honest. Okay, 1 minute. Yeah, I can understand that this is 90-degree, right? Which means that this angle is supposed to be what, 180 minus 90 minus 40.5, which is 49.5 degree. If this is 49.5 degree, this over here is going to be 90 minus 49.5. This is again 40.5, right? Wait, why is it again 40.5? 1 minute. Yeah, that's because they were creating um, alternate segment, alternate angle. This is also 40.5. If this is 40.5, this is again 40.5, right? And hmm, this is again 90-degree. One thing to understand, I'll have to extend these lines a bit more so that these two normals will actually be perpendicular to each other, which means if this is 40.9, this is going to be again 49.5, and this is going to be 49 point, okay, this is again going to be 40.5, right? And sorry, this is again going to be 49.5. 49.5, and then again over here we're going to have 90-degree. You can add these calculations as part of your working over here, and yeah, and arrows over here is supposed to be drawn. This is how the arrows are supposed to be drawn. Okay, if it's not clear, I will actually write it down in a much more clear diagram. This one is 49.5. Okay, I calculated that by subtracting 180, 90, and this one, and then again this part is 90-degree total. 90 minus 49 is again 40.5 degree. And as it was total internal reflection over here, it was also creating 40.5 degree, right? They will both have the same angle. And then again, using the 90-degree, this 40.5, this one turns out to be 49.5. This one turns out to be 49.5, right? And the others one are 90-degree as they move out of this like diamond shape, right? And then again explain what would happen to the ray as it at this boundary if the material used was silicon carbide instead of diamond. If you go back to these places, okay, as you can understand that the speed of the light is greater in diamond than in silicon. That means obviously silicon must be more dense, right? That's why the speed of light is less in silicon carbide. So if it has more density, that means your object was moving with smaller speed, right? Higher density means the entire light will be deviated at a smaller angle, so they will be creating smaller angles inside the structure. So we can write uh, silicon carbide has higher density, so angles at boundary would be smaller. Would be small. Okay, this is your answer. And this one is a very important question. This came out to be a question from Jan 2020. It says that there was a gap in between the steel bar and we are using a transducer to detect the gap. Explain how the arrangement can be used to show whether the RJs contain an air gap or not. So what happens over here again, I will measure that entire length of the RJs, right? RJ is basically this steel gap they're referring about. And in this steel gap, okay, or in this steel bar, it will obviously not reflect from the surface because we are providing some kind of gel or something in order to prevent reflection from the steel to the air boundary. So most of this ultrasound will be will be entering inside the steel bar. And what happens over there, if there is a gap in between them, there will be a change in density again. Steel has a steel density and gap has an air density. Due to this decrease in density from steel to air, this ultrasound will be reflected, and that reflected ultrasound will be detected by the transducer again. And using that detector, using that reflected transducer, it will also automatically measure the time that was taken by the pulse to be transmitted and received. Using the time and distance, so time and when basically using the time, this entire transmission and detection measures twice the time, right? Once for going and once for coming back. So using the twice the time, and I already know the velocity for ultrasound in speed, so using that I can find out the distance. If it turns out to be the distance is less than the actual width of this RJ steel block, then obviously there was a gap at some position in between the steel block, right? This is how you're going to arrange your answer. So let's start with this. I'm just going to write that ultrasound enters the RJS steel bar, and if there is a gap, there will be a change in density. Due to this, rays will be reflected, which are received by the transducer. Okay. Now again, the transducer measures the time taken for the wave to be transmitted and reflected and detected and received by the transducer, which measures the time taken for the wave to be transmitted and reflected so undetected. Using this time measure distance with Vt over T. So if measured distance is less than the wideness of this RGS tail bar, then there is a crack, right? So we can write finally that yeah, we don't need to identify the result. We just need to explain how this arrangement can be used to show whether the RGS contains a gap or not, right? No, actually, we have to write down the final statement also, that if measured distance is smaller, then if measured distance is smaller than RJS thickness, measured than thickness of RJS, gap is present. This kind of question again arrived in the recent papers. I think it was May 23 or October 23, right? A similar kind of question was there, and a star mark question it was, right? So I would suggest, go through the previous years and see that which year has this big kind of descriptive question. And these kind of descriptive questions could appear in your paper as a star mark question, because again, as I've stated, they do not have much, like different theories to ask this kind of descriptive questions from. The pattern will be repetitive for unit 2. Okay, so moving to this part, it says that ultrasound is a sound wave with a frequency greater than 20 kilohertz. The frequency of ultrasound used by the transducer in this method is 5 megahertz. Explain why a much higher frequency than 20 kilohertz is used in this method. Because higher frequency gives smaller wavelength. Smaller wavelength means there will be smaller chances of diffraction and higher resolution for the scan, right? And higher resolution means that more details can be detected from this scan. So yeah, that is the answer, that higher frequency gives smaller, higher frequency gives smaller what? Higher frequency gives smaller wavelength, so less diffraction. If there is less diffraction, that means higher resolution. Therefore, higher resolution. Okay. Now after this is a diffraction grating part. They have dx, this distance, determine the wavelength of the light from the laser after the maths. Okay, this is actually the last question from this part. Okay, we need to measure the wavelength of the light from this laser, and at some point diffraction grating should also be given. 1 minute. Mm. When the laser is switched on, a series of bright dots is seen on the screen. The diagram shows the position of a center dot O, and the next dot appears at this. Diffraction grating has, yes, this one, 450 lines per millimeter. Using that, you can find out the value for small d, right? And I do not have much space. Okay, so that small d is basically going to be like, since you have what, 450 lines, all the other lengths are in meter, okay, and you have to find out the wavelength also in terms of meter. So let's just find out that how many millimeters are there in 1 meter. That is basically what, um 100,000, right? 1000. So 450 lines in one, wait, in 1 millimeter, right? This is going to be 1 over 10,000, 1 over 1000, right? 1 over 1000 meter. In that case, in between one line, that is the value for your d, is going to be 1 over 1000 divided by 450, which is going to be 1 over 1000 divided by 450, which is 1 over 450,000. Okay, I'll just write it like this, 1 over 450,000. Okay, this is a value for your small d in meters. Now using this, I can find out the value for theta easily. That is what? 0.5 divided by 1.69. So theta is going to be tan inverse 0.5 divided by 1.69, which is 16.5 degrees. Okay, now then again, using this theta as a value for your theta is 16.5 degrees. Now I can find out the value for your what? Lambda, because over here value for n is 1, right? So you can use that n lambda is equals to d sine theta. So lambda is going to be d sine theta. So sine is 16.5 and divided by it will be this 450,000, which is sine 16.5 divided by 450000. That is 6.31 into 10 to the power of negative 7 meter. So 6.31 into 10 to the power of negative 7 meter. Also, you can write this in terms of 631 into 10 to the power of negative 9 meter, which can be written as 631 nanometer. Right? Both over here can be written. Okay, now explain why a series of bright dots is seen in the screen. Repeated question, right? Waves are going to interfere constructively where they are in phase when their path difference is n plus half lambda. And so n lambda over here, right? That is the final answer. Very, very repetitive question. We have did this quite a lot and we're still doing this. So over here, the answer would be that waves from the different slates meet and interfere, and interference takes place. Interference takes place at bright points interfering constructively at bright points. The waves are interfering constructively. Um, the waves are interfering constructively. 1 minute. The waves are interfering constructively when they are in phase and have path difference of n lambda. Okay, that is the final answer. The laser is replaced by a source producing a parallel beam of light, sorry, beam of bright white light. State what would now be observed on the screen. Now dispersion would occur, right? Because white light is composed of 7 different colors. During diffraction, when this light will be traveling through the white gaps, through the gaps between the lines on the diffraction gratings filter, then they will get diffracted. During diffraction, what happens? During diffractions, they are going to have, they're going to travel at different speeds. So now the 7 colors will disperse and the dispersion effect will be now seen, right? So we can write that white, we can see that, okay, we can create only white dot at the point O, and all the other cases we will see the diffraction pattern, right? The spectra will be seen on either side of the dispersion because diffraction causes all the 7 colors to travel at their individual speeds, separate individual speeds. So you can write that white dot will be seen at O and spectra of 7 colors on either side, sorry, will be seen. We just need to suggest, not explain. So I think writing this much is enough. If the question was about explaining, then I would have written that extra part, that during diffraction, all the lights will travel to their own individual speeds. That's why the dispersion will occur, right? But since they're not asking about an explanation, so let's not write about explanations over here. And light is a transverse wave. Describe the difference between transverse and longitudinal waves. Quite easy, right? We know that in transverse wave, the direction of propagation is perpendicular to the direction of wave travel, and in longitudinal wave, direction of propagation is parallel to the direction of wave travel. That is your final answer. So I'm going to write that in right, this is the answer then, and I think this is a very common answer from our IGCSE physics, right? This is a repetitive question again, but I would not suggest memorizing it. I hope by this time we all have this already memorized. Okay, so yeah, this is it for your waves. All the things we did for the entire waves. Right, we solved quite a lot questions to be honest. In average, I think there are approximately 50 questions, including the MCQs and the detailed answers. Okay, and even after this, if you guys think there is any problem, contact me in WhatsApp or this entire file. If you guys want this, please join our Discord group. The link of the Discord group will be attached in our description boxes. So I would suggest go to that link, join the Discord group, and get access to this file, both written and empty. So yeah, thank you for watching. I would suggest all the best for your exams, and if there is any way I can help, please let me know. Thank you for watching. Bye bye.